Welcome to the fascinating world of 5G and its backbone, electromagnetic waves. Electromagnetic waves are a fundamental physical phenomenon, carrying energy and information across the globe and making modern wireless communication possible. To better understand electromagnetic waves, we'll begin by introducing the electromagnetic spectrum. Imagine it as a huge, multi-lane highway. Each lane represents a different type of electromagnetic wave, such as radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. These waves are categorized based on their frequency and wavelength, forming a continuous spectrum from low-energy, long-wavelength radio waves to high-energy, short-wavelength gamma rays. Radio waves, with frequencies below 3 GHz and wavelengths ranging from kilometers to tens of centimeters, are the longest and least energetic waves in the spectrum. Their long wavelengths allow them to travel great distances and penetrate obstacles like buildings, making them ideal for long-range communication. They are widely used in AM and FM broadcasting, GPS, television transmission, and mobile communication. Microwaves, with frequencies between 3 GHz and 300 GHz and wavelengths from centimeters to millimeters, carry more energy than radio waves and offer greater data transmission capabilities. Their shorter wavelengths allow them to be easily focused and directed using antennas, making them highly efficient for wireless communication. Microwaves are commonly used in Wi-Fi, Bluetooth, satellite communications, and mobile networks. In household applications, microwave ovens use specific frequencies to excite water molecules in food, generating heat through molecular vibrations. Moving into the mid-frequency range of the spectrum, we encounter infrared waves and visible light. Infrared waves, with frequencies ranging from 300 GHz to 430 THz, have shorter wavelengths and carry more energy than radio waves and microwaves. They are emitted by all warm objects, making them useful in thermal imaging, remote controls, and fiber optic communication. Visible light, with frequencies ranging from 430 THz to 750 THz, occupies a narrow band of the electromagnetic spectrum. It is detectable by the human eye, allowing us to perceive colors from red with its longer wavelength to violet with its shorter wavelength. At the high-frequency end of the spectrum, we enter the intense region of ultraviolet waves, X-rays, and gamma rays, characterized by their high energy and short wavelengths. UV waves, with frequencies between 750 THz and 30 petahertz, are essential for sterilization and vitamin D synthesis, but can cause skin damage with prolonged exposure. X-rays, ranging from 30 petahertz to 30 exahertz, can penetrate soft tissues, making them invaluable for medical imaging. Gamma rays, with frequencies above 30 exahertz, are the most energetic waves produced during nuclear reactions and astronomical events. While they're vital in cancer treatments and deep space observations, their intense energy requires careful handling. But where exactly does 5G sit within the vast electromagnetic spectrum? We've learned that higher frequency millimeter waves enable faster data transmission, carrying more information. However, due to their shorter reach, they require transmitters to be positioned closer to the receiving devices to ensure seamless connectivity. The radio frequency spectrum is divided into 3 main bands. Low band, typically ranging from 600 MHz to 1 GHz, provides extensive coverage and excellent penetration through obstacles like buildings, making it ideal for broad, reliable connectivity. The mid-band, spanning from 1 GHz to 6 GHz, balances coverage and capacity, offering faster data rates while still covering large areas. The high band, or millimeter wave, includes frequencies above 24 GHz, supporting ultra-high data rates and capacity, but with limited coverage and greater susceptibility to obstacles and atmospheric interference. These frequency bands have been utilized by wireless technologies across generations to enhance performance. 1G, the first generation, operated around 800 MHz in the low band, providing basic analog voice services with limited capacity and coverage. 2G moved into the 900 MHz and 1,800 MHz ranges, entering the mid-band and offering improved voice quality along with basic data services like SMS. 3G expanded its use of both low and mid bands, with frequencies around 850 MHz, 900 MHz, 1900 MHz, and 2100 MHz. This enabled mobile internet and video calling, marking a significant leap in data capabilities. 4G further advanced connectivity by using frequencies from 700 MHz to 2600 MHz across both low and mid bands, delivering high-speed internet suitable for applications like HD video streaming and online gaming. 5G revolutionizes the spectrum by utilizing a broad range of frequencies. In the low band, it operates between 600 MHz and 700 MHz, ensuring wide coverage with moderate speeds. In the mid-band, it typically uses frequencies between 1 GHz and 6 GHz, especially around 3.3 GHz to 3.8 GHz, achieving an optimal balance between speed and coverage. Finally, in the high band or millimeter wave spectrum, 5G operates above 24 GHz, enabling ultra-high speeds and low latency for data-intensive applications. However, these high-frequency waves have a shorter range and are more susceptible to interference from walls and buildings. In summary, each generation's use of frequency bands reflects a steady progression toward higher frequencies to meet growing demands for faster data rates and greater capacity. 5G, operating in the radio and microwave parts of the spectrum, particularly excels in the millimeter wave range. While these frequencies enable unparalleled speeds and low latency, they require innovative solutions to address their range and obstacle challenges. This evolution in frequency utilization highlights the transformative potential of 5G and its role in shaping the future of connectivity. To wrap up this video, let's take a quick look at the key core technologies driving 5G. One of the most exciting technologies behind 5G is Massive MIMO, multiple input, multiple output. Picture a crowded airport where everyone is trying to talk to the airline representative at the same time. If only one counter is available, it'll be chaotic and slow. Now, imagine if there were multiple counters, each handling a different group of passengers. Massive MIMO uses multiple antennas to handle more data at once, like having many airport counters to reduce congestion. This ensures 5G can support more users simultaneously without slowing down. The next 5G technology is beamforming. Imagine you're at a restaurant and the waiter is delivering food to tables. Instead of shouting out orders to everyone in the room and hoping the right person responds, the waiter goes directly to your table and places your order in front of you. This focused approach ensures you get exactly what you need without confusion or delay. Similarly, beamforming in 5G sends the signal directly to your device instead of broadcasting it in all directions. For instance, if you're in a crowded park streaming a live sports match, beamforming ensures the network focuses its signal on your device, giving you a smooth and uninterrupted viewing experience, just like the waiter delivering food straight to your table. Network slicing is another interesting technology used in 5G. Imagine a massive warehouse with different sections. One for storing fragile items that require careful handling, another for high-demand products that need quick access, and a third for long-term storage where items are rarely retrieved. Instead of having one giant space for everything, each section is organized and managed based on specific requirements. Network slicing in 5G works similarly. It divides the network into separate virtual sections, each tailored for a specific purpose. For instance, a critical medical application requires ultra-reliable and fast connections, while a smart sensor might only need minimal bandwidth. Network slicing ensures each service gets the right type of connection without interference, just as the warehouse ensures each item is stored appropriately. The final 5G technology we will discuss is edge computing. Picture yourself driving an autonomous car, and suddenly, a pedestrian steps onto the road. The car has to react instantly to avoid an accident. Edge computing makes this possible by processing data near the car on the edge of the network, rather than sending it far away to a central server. This reduces the time it takes for the car to make a decision and speeds up the process of reacting to the environment. Edge computing brings similar real-time responses to other applications, like industrial robots or remote surgeries, where decisions need to happen instantly. These technologies are what make 5G more powerful, faster, and capable of transforming our daily lives. While 5G promises transformation, it faces key challenges. Infrastructure costs are a major concern. 5G's high-frequency bands, such as millimeter waves, have limited range and require dense networks of small cells, antennas, and advanced fiber optic backhaul. Deploying this infrastructure is particularly challenging in rural and underserved areas where low returns on investment may not justify the expense. Spectrum allocation is another significant challenge. 5G demands access to a wide range of frequency bands, from low bands for coverage to high bands for speed. Coordinating spectrum allocation globally involves regulatory hurdles, such as potential delays and conflicts among governments, telecom operators, and industries. Security and privacy also pose critical challenges. The increased number of connected devices and reliance on 5G networks amplify the attack surface for cyber threats. Reducing risks like unauthorized access, data breaches, and network vulnerabilities requires strong encryption protocols, real-time threat detection, and secure device authentication mechanisms. In conclusion, 5G is more than just faster internet. It's a transformative force reshaping industries and enabling technologies that once seemed like science fiction. Thanks for watching, and if you enjoyed this tutorial, please like, share, and subscribe to stay updated. We'd also love to hear your thoughts in the comment below.